Okay, this is video 2 for the electricity basics quiz. In video 1, we talked about what is electricity. We mentioned protons and electrons and electric fields. We said we were going to skip this idea right here for the most part. We haven't talked about static versus current yet. We did talk about current and what makes a circuit, and we talked about conductors and insulators. So that means what I have left to cover in this video, I've got to talk about static versus current and AC versus DC. So here we go. AC versus DC is where I think I'll go first, because if I remember properly, we finished the last video talking about this. A battery makes electricity that flows in one direction. And if it only flows in one direction, we call that direct current. That is how a car battery works, or a flashlight battery. The current, the electricity, the electrons go just one way through the wire. That's it, one way. And a long time ago, when people first started using electricity, this was how we made it. We used direct current. And direct current is nice. I mean, it's actually awesome, but there is a big drawback. The drawback with direct current is it's not good for long distances. If you want to send electricity more than a few blocks, you need so much voltage that you're going to start burning people's houses down. It's going to be a bad thing. I just use a science word, voltage, and voltage is just the push of the electricity. So if you have a 1.5 volt battery versus a 12 volt battery, the 12 volt battery has more push to it. And for now, that's good. So direct current is great, but it's not good at going a long ways. Well, how do we send electricity a long ways? Because I'm pretty sure where I live out in the woods in Sanford, it's not direct current coming to me. It's got to be something else. So a long time ago, this really smart guy named Nikola Tesla came up with another idea. And here's Nikola Tesla's idea. I want you to imagine that we've got these two spools here. What's a spool? It's just like a hollow cylinder that we use to wrap thread on. Imagine that you've got two spools and you've got this string that goes around both spools and it's tied into a loop and it comes back. So you've got this loop of string. So this is an analogy, and think about this. If my goal is to spin this spool and make this spool spin, I've got two choices. What are my two choices? I can just move this one spool continuously clockwise, and that will move the thread around, and it'll just keep going clockwise. That's option one. That's like direct current. But Nikola Tesla came up with another idea. He said, well, why do we have to just spin one spool in one direction? Why don't we just take this one spool, move it a little bit this way, and then spin it back a little bit this way? So if you looked at our piece of yarn here, or string or whatever, it's going to go this way a little ways and this way a little ways. So that going back and forth, that's what we call alternating current. And the nice thing about alternating current is it can go long distances very, very well. So in this analogy, this spool is kind of like the power plant. That's where we put our energy in. And this spool is kind of like me at my house. I'm using the electricity. So alternating current, very good at going great distances, and that's why we use it. So you've probably got it in your head that, yeah, I can kind of understand how a chemical reaction can make current go one way in a battery circuit. How do we make alternating current? Well, here's how we do it in our society. What we do is we take these two magnets, and magnets have a magnetic field going between them, and we use some method to spin this crank. You might use a waterfall. Like in Beaverton, we have a dam, and the dam spins this turbine around. So imagine instead of a crank here, you've got this a bunch of fan blades, and the water moving over it makes this spin. And when this spins, this loop of wire, this loop touches this piece of metal, this collar, and this end of the loop touches this collar. And as the loop spins around, it sends electricity in one direction, and then it sends electricity back in the other direction. That is what we call alternating current. I can't go into more depth with my crappy drawing here. If I do, this video will be way too long. So the last thing I want to talk about in this video is static versus current. Well, we talked about current. Now we need to talk about static electricity. So what is that? Static electricity is very easy. Static electricity is simply separated charges. That's it. So if you have a positive next to a negative, they add up to be neutral. They add up to be 0. Okay? That's fine. And if you take them and you separate them, you move the positive over here and maybe move the negative over here, now they want to get back together because opposites attract. We call that voltage. So if you separate charges, you build up voltage. You build up that push that we talked about. So I drew 2 examples here. We've got this balloon, and it's got protons and electrons in it. I'll just draw 2 of each. And we've got this hair. And this hair is also neutral. It's got, for every plus, it's got a minus. So I'll just draw 2 of each. If you take the balloon and rub it against someone's hair, what happens is the charge separates. Some of these negatives that were in the balloon go into the hair. So I think I just said that backwards. I did say it backwards, and I'm not reshooting this video, so I'm going to fix it right now. Some of the electrons from the hair actually go into the balloon. So now the balloon, instead of having 2 pluses and 2 minuses, now I've got 2 pluses and 3 minuses. Well, what does that mean? That means the hair still has its 2 pluses, but it's only got 1 minus. So now the hair is overall positively charged, the balloon is negatively charged, and since each hair is positively charged, that's why it stands up and tries to repel itself. And if you wave the balloon around your head, your hair will point at the balloon. So before we had our electric charge not separated, when we rubbed the balloon on the hair, then some of the electrons went into the balloon, and that left us with separated electric charge. The hair was positive and the balloon was negative. So let's talk about lightning then. Inside of a lightning storm, what happens is separation of charge. And I don't understand why. I don't think scientists understand it too well yet, but they're working on it. What happens is the bottom of the cloud builds up a very negative charge, and the top of the cloud builds up a very positive charge. Well, this distance is pretty great from the bottom to the top of a cloud. That can be like 5 miles. So as a cloud blows across the land, what happens is, remember, electrons can move and protons can't in solids, so the ground is solid here. These negatives in the bottom of the cloud are going to repel the negatives further into the ground. So as a lightning cloud goes over and you're standing on the ground that you're standing on has a positive charge. And so if this cloud is blowing along, and let's say you have a house that has this positive charge built up, this building up of charge we called induction. I'm going to say that's induced charge. And as this cloud goes over, if it gets close enough, then you can get a lightning strike. And then that is definitely not static. That is current. But the simple idea of static electricity is separated charges. Yes, static electricity can move. We saw that with both of these examples. And I'm almost at 9 minutes, so this video should be over before you fall asleep.